Yay! Great. So again, lovely to see you all. Really nice to have you back. It feels like we haven't seen each other for forever. Um, so basically, the second half, not basically, the second half of the course is going to build on what we've done in the first half. But notably, everything that we're going to do from now on, everything that we're going to do from now on, that's the stuff I'm going to test you on in the midterm. Right? So, or sorry, Jesus, the final exam. Right? Hi, paying attention. Um, so that is the stuff that we did in the first 7 weeks. That's the material for the midterm. The stuff that we'll do in the next 6 or 7 weeks, that's what's going to be on the final exam. So in particular, what I want to do today with this lecture is a little bit like a palate cleanser. So you know how you get the ginger whenever you order sushi, and you're supposed to have that like in between to kind of like rinse out the taste so you can get the full experience from each type. That's basically what this lecture is. This is kind of a something completely different as a kind of intermediate stage, because there's always sometimes a literal, sometimes a metaphorical hangover right after the midterm. So this is a little bit of palate cleanser, a little bit of hangover cure, in order to set us up to go on for the big stuff we're going to do for the rest of the semester. So really what this lecture is about is introducing you, or perhaps re-familiarizing you with, some basic set theoretic machinery. I want to stress that this is not a set theory class. It'd be super cool if it was, but it's not. So really my aim here is just to kind of introduce you to some notation and some fundamental concepts, so that when you run into this stuff later on, you'll at least be sort of prepared for it. So the core focus of the second half of the course is going to be extending our formal toolkit. As I said, this week is basically our palate cleanser on set theory. And then from then on out, what we're going to do is just work on natural deduction. So we'll talk more about what exactly that is in the next lecture. But broadly, natural deduction, especially when it comes to FOL, it's the kind of complement to our semantic machinery. So if you remember, for first order logic, there was a whole bunch of things we couldn't do with interpretations. Natural deduction is the tool we use for all of those cases. So really, it's interpretations plus natural deduction that gives you your full formal machinery. So that's what we're really going to focus on. And that's going to be the bulk of what we'll do. But today, we're going to do some set theory. And I should stress, because there's only 13 weeks this year, we won't do any meta logic, but that's okay. I've got a recording if people are interested in that, or you can come talk to me about it. It's totally fine. Right. So for today, the plan is, again, to go through some really basic ideas about what set theory is and set theoretic notation. We'll talk about Russell's paradox. Are people familiar with Russell's paradox? Have you heard of it before? It's like basically the barber who shaves all and only himself, right? Yeah, you've heard of this, right? So we'll talk about it and talk about the kind of upshots that Russell's paradox has for set theory. Then I want to talk about relations. So in particular, I'm going to throw a bunch of different definitions, notions, concepts at you about types of relations. So I'll try and flag the ones that we're really going to be focusing on, but this is, again, to introduce you to some terminology that I suspect you'll run into later in life, and I want to be sure that you've at least heard it before. And finally, if we have some time at the end, we'll have some fun and just joke about degrees of infinity. So we'll talk about Hilbert's Hotel. Have people heard of Hilbert's Hotel before? Yeah, okay, cool. Yeah, so we'll talk a little bit about that maybe if there's time. Again, that's just for sort of funsies. It's not going to be anything I'm going to examine you on. So that's the plan for today. Let's go through some basic set theory. So the core idea, if you like, when we're thinking about set theory is, how should we think about collections of entities? Right? So if we think about all the people in this class, well, we can think about them in terms of the specific individuals, but we can also say things about the collective that seem true of the collective, not of the individuals. So I think there's about 190 people registered for the course. So I can say there's 190 people in the collective. That's certainly true of the collective, but not of any one of you. You're not 190 people, you're one person, right? Similarly, we can talk about the people who live in my house, right? Mira, my wife, myself, right? We can say, hey, there's 3 of them, but of course none of us are 3, we're all 1. So whenever we're thinking about collectives, right, there's times when we actually want to talk about the collection itself, not just kind of go through it or have it as a roundabout way to talk about the constituent parts, the members. Right? And the intuitive thought here is that whenever you have a collection of entities, there's a distinct thing that is the collection. Right? Things will make up the collection. They'll be part of it in some sense of part, but the collection is something over and above the individuals. And this is a rough and ready idea, right? You might push against it, but there's something intuitive to it. Right? And set theory effectively formalizes this intuitive idea. And it formalizes it in a highly rigorous, really lovely way. And it's notable, set theory is used everywhere in mathematics. Right? And it's used everywhere in mathematics because basically it treats collections as just other mathematical objects. So collections aren't just sort of weird, spooky additional things. They're just more stuff. They're just stuff that stands in special relations to other stuff. And once you have that, well, cool, we can start talking about the collections themselves. They're just more grist to our mathematical machinery mill. So, some terminology. We'll say that a set is a collection of things considered as a whole. Okay? And the members are the things that are collected together into the set. Right? So if we take the set of people registered for this class, then each one of you is a member. Right? And we can talk about individuals, or if we're going to be fancy-dancy, we can talk about elementa. Right? These are the things that are not sets that can be members. Right? So physical objects, my pointer, my phone, all of us, right? We are elementa. That is, things that aren't sets that then can be fed into set construction machinery. Right? The elementa, the individuals, are the stuff that you start with before you start making your sets. Now, of course, right, there's a relationship between individuals or members and sets, and that is membership. Membership is a special relation. It is literally just the relation that holds between a member and the set is a member of. We express it with this little symbol that looks a bit like the euro sign. Right? So this is to say that Mira is a member of the set of dogs that live with me. And then if we draw the line through it, this tells us is not a member of. Right? So Mira is not a member of the set of people in this room, which is good because she doesn't deal with new people very well. She'd probably bite someone. It's probably for the best. Right? So again, this expresses the membership relation, and it's the relation that objects or things stand in to the sets they are members of. Now we can denote a set using a singular term. We could do it with a definite description, like I did here, right? This set of dogs that live with Nathan. Right? Or we can just list off the set by using the curly brackets. And this is why we couldn't use them before. Right? Remember I said, hey, you can use whatever brackets you want as long as you don't use these ones. That's because these ones are special. Whatever we list in between these, we're saying, hey, these things are members of the set we're talking about. So Mira is a member of the set whose members are Mira and Darth Vader. Right? Nathan is not a member of that same set. And we'll talk more about exactly what's going on in here, but again, this is just to kind of familiarize ourselves with the notation. So again, you have sets, these collections. You have members, that is the things that are parts of or constituents of the sets. And you have individuals, stuff that isn't sets. Now the core idea when we're thinking about sets is an axiom of extensionality. This tells us what their identity conditions are. That is, when are two sets identical and when are they distinct? And we'll say that two sets are identical if and only if they have all and only the same members. I formalized it here, right? So set S is identical to set T if and only if for everything it's a member of S, it's also a member of T, and vice versa. So again, two sets are identical if and only if they have all and only the same members. On the flip side, two sets are distinct if they have at least one different member. This is really the core of pretty much every set theory. There'll be other axioms that we can kind of play around with. We'll talk more about this when we get to Russell. But this is the big basic idea when we think about sets. They're individuated by their members. One other thing to note here is that when we think about their members, we don't think about how they're named. We just think about what objects they are. So for example, right, these two, they're the same set. The fact that we listed Socrates and Plato in one order and then in a different order doesn't matter. You can think about these as like bins, right? They're unsorted bins. We don't care about the order that you threw them in. They're all in the bucket. Similarly, these two sets are identical. And that seems weird because you might think that, hey, there's two over here and one over here, but why are these sets identical? Well, how many objects are actually over here? Yeah, one, right? Clark Kent is Superman. Oh, shock, right? These are the same object, right? If it turns out that these two names refer to the same object, then really there's only one object in here. And hey, it's the same object over here. That's his original Kryptonian name, for those who don't know. Right? So one thing that kind of comes up here, right, is the list that you write down in the membership thing might not be a perfect list. You might have more names than the actual objects you have. Sometimes you have to do some digging. And we can do some more notation, right? We can say the set of all things X such that, so this is just to say the thing X is that, and then we put some FOL sentence in here. So is an F, or is an F or a G, et cetera, right? So for example, we can say the set of all happy things, we can list this way. And implicitly, there's a universal quantifier here. In fact, set theorists are frequently very bad about this. They leave off the universals. It's annoying. You should list all of your notation. Okay, so again, the big thing here to know the axiom of extensionality, this is something I'm going to probably ask you about, right? Something to know. So some things about the membership relation and generally how these go. Individuals stand in membership relations to sets, right? So Socrates, the individual, can be a member of or is a member of the set containing Socrates and Cicero. However, nothing stands in a membership relation to an individual. And that makes sense because remember, we said, what are individuals? Well, they're things that aren't sets. So they can be on the left-hand side of the membership relation, but they are never on the right-hand side. They can be members of, but they never have any members. Interestingly, though, sets can also be members. Sets can be members of other sets. Right? So, for example, the set whose members are Socrates and Batman is a member of this set. And this highlights another thing about the notation. Right? Note what we have, the outermost brackets telling us, okay, this thing is the set we're talking about. And this set has two members. And its two members are two sets. This one, the one with Socrates and Batman, and this one, the one with Cicero and Superman. So we have to be careful about the number of times we put the little curly brackets. If you put them once, right, you've got one set. If you put another pair, well, cool, you've got a set with a set inside. Now that is kind of weird, but does everyone get the idea there, right? So this set over here has no individuals as members. The big one. It only has two sets as members. In turn, those two sets that are members, well, they both have individuals. Yeah.
Could we say that a set of Batman and Cicero would be an element of
the big one? Yes, yes, yes. It's a member, right? We can talk about it being an element or a member. Either bit of terminology is perfectly fine there.
I mean, the set Batman and Cicero.
Yes.
Together. Would it be a set of, can we separate those sets?
Yes. Yes, yes, yes. So we can talk about this one. So we'll call it the sock bat set, right? The sock bat set is a member of the bigger set, right? Or also we can talk about this thing, this sock bat set being an element of the big set. Either way is perfectly fine.
Batman Cicero set, an element of the big set.
Yeah. So importantly, again, what we're really interested in here is just getting clear on this notation, right? If it's just got the one bracket, like over here, right, then basically we're just thinking about what's in this bin. And then if you have stuff that's in a bin, right, well, then you don't go inside that. You just stop at the outermost level. It's like there's a box inside the box. Cool. What we're counting is then just the boxes, the ones in there, not what's in those. So a question we'll come back to. So again, the big idea here that I want to get across. Individuals can be members of sets. Sets can be members of sets. One question we'll come back to. Can a set be a member of itself? Probably, but we'll talk about it. So we have membership, right? Membership is what it is to be a member of, to be an element of a set, to be in the collection. There's another relation that we can talk about here, which is subsethood. Subsethood is a relation that two sets can stand into each other. And we'll say that set S is a subset of set T if and only if everything that's a member of S is a member of T. So the idea here is actually quite straightforward. And in fact, it's almost given away by the symbol. The symbol is very close to less than or equal to. And that's the idea. So to go back a slide, if we look at this set here, Socrates, Batman, that set, right? This set whose member is just Batman is a subset of this. Why is it a subset? Because all of the members in our set containing just Batman are also in the set with Socrates and Batman.
If we put another bracket around Socrates and Batman, so it's a set containing Socrates and Batman, would we say that it's a subset of the next one?
Good. So cool, right? The set whose member is only Batman is not a subset of this one. Because Batman is not a member of this big set. So again, the reason why, think about it in terms of boxes, right? This thing, the big set over here, only has two members. And its two members are this box and this box. And it doesn't look inside those boxes. It just stops there. It's like, cool, I've got two. It's this thing and this thing. Yes?
So the difference between a member and a subset is just the amount.
Good. So this is something I want to keep. This is the big concept thing. The difference between membership and subset. Membership is a relation that individuals or sets can stand into a set. It's to be part of the collection, right? Subsethood is to be a collection that is smaller than another collection. So here's an example. Take the people who are in tutorial group 3. Those people are a subset of the people registered for the class. That is, they're part of the bigger collection, but it's a collection. Whereas there's no particular person, no individual, who is a subset of the people registered for the class. Because individuals aren't sets. You've got to be, to go forward a slide, a collection that's smaller than, less than or equal to. So again, we can kind of drive this home with an example. So suppose we have a set whose members are A, B, and C. Right? If we're thinking about this set, now compare it to this one, right? Take the set whose members are A, B. This is a subset of this collection because everybody who's in here is also in here. But it is not a member. This is not a member of this collection. Yeah.
So for example, even if you take every element, but you're just missing one or more, that means you now have a subset of that list.
In fact, you don't even have to drop any elements. Because to be a subset is to be less than or equal to.
Or equal.
So that's a nice thing. Every set is a subset of itself. Right? Because to be a subset is just to be a smaller than or equal to sized collection. So ABC, right, this set here, that's a subset of itself. It's less than or equal to. Right? Now you might be interested in just what's strictly less than, right? This is why we have the notion of proper subset. Proper subset is strictly less than. And again, you can see it with the way we do the notation. Subset is less than or equal to, right? Proper subset is just the less than. And to formally express proper subset, we'll say, okay, cool. S is a proper subset of T if and only if every member of S is also a member of T and they're not identical. By adding this extra bit, we force it, because of the axiom of extensionality, we force T to have at least one more member. T's got to be strictly bigger. So again, we have two fundamental relations here. Membership, which is to be a part of the collective, to be in the collective, and subsethood, which is a relationship between collections. Yes?
I don't understand why ABC is not a member of ABC because they are in
Good. So importantly, when we're talking about it, we talk about this thing. The collection, the set itself, is not a member of that set. Its members are, sure, right? But is this box itself inside this?
So if it has brackets inside the left part, it would be a member.
Yeah. If we wanted this to be a member, we could do this. But interestingly, now, this is a member, but it is no longer a subset. Why is it not a subset? Because its members, A and B, are no longer in this.
So something cannot be a member and subset. So something cannot be a member and a subset at the same time.
It can, but importantly, you have to satisfy two conditions then. First, if you're a subset, that means everybody who's a member of you is also a member of the one you're comparing yourself to, and you stand in the membership relation. you've got to do both to do both. Again, the important thing for membership is just you're a part of the collection. Subsethood is everyone who's in my collection is also in the other one. Yes?
So if we took this set and we added two elements, A and B, it would now be a member and a subset?
Yes. So now, if we look at our collection now, right, our big collection, and compare it to AB. AB is a member because it's right here. It's also a subset because its two members are in here too.
Could you raise the board?
Yeah, sorry. Better. Okay. So again, this kind of conceptual point, I think, is really, if we can get the difference between membership and subsethood, you've got the deepest, darkest point about set theory. So again, subset just means less than or equal to, right? Everyone who's a member of the first one's also a member of the second one. It could be the same set. Proper subsethood means strictly smaller than. Right? Okay. So we mentioned this already, but every proper subset is a subset. Right? Everything that's less than is less than or equal to, but not the other way around. And that's because the limit case of being a subset is just being identical. That is, having the exact same members. And in fact, one thing that's interesting is we can also say that two sets are identical if and only if they're subsets of each other. Because if you have two things that stand in the less than or equal to relation to each other, well, the only way that could work is if they're equal. Okay. So again, we've got membership, we've got subsethood. We can also define the more strict proper subsethood. We can also define the inverse relation, which is superset. Superset is, unsurprisingly, just greater than or equal to. It's the other way around. S is a superset of T if and only if T is a subset of S. Right? And again, you can see it in the notation, right? If the other one was this way, right? If subsethood was this way with a line underneath it, superset is, hey, greater than or equal to. And just like with being a subset and a proper subset, we can define superset and proper superset. And much like how I told you a second ago that every set is a subset of itself, every set is a superset of itself because everything is greater than or equal to itself. Yeah, sure. So we can think about these two, right? Again. So this one is a subset of this because A and B are both members of this bigger set. Conversely, this is a superset of our small one because it's got all of these members and some more stuff. Again, literally just think about it in terms of, hey, does it have everyone who's in the one group? If you're thinking about the smaller one, then it's subset. If you're thinking about the bigger one, it's superset. Again, terminology, this is stuff that probably will come back much more often in later stuff, but it's useful to know it now. Okay. So that's the kind of core mechanics. We'll talk a little bit more about some other things, but I want to talk to you about some basic sets and set ideas. So a little bit of terminology again. We can talk about unit sets or singletons. These are sets that contain only one member. So for example, you have singleton Socrates, singleton Plato, or this one. What's the one member of this set? Yeah. This is singleton Socrates, the set whose one member is the one-membered set with only Socrates as a member. Again, do you guys familiar with the notion of semantic satiation, where you say a word so many times it starts to lose its meaning? By the end of this lecture, the word set will be like that. I'm so sorry. There's just no way to do it, unfortunately, that isn't like that. It just happens. So, okay, again, a unit set has one and only one member. At a singleton, I'll also talk about being a singleton. We also have the empty set. The empty set is the set that has no members. Right? Let me just repeat that. The empty set is the set that has no members. It is the collection of people who love you. Oh, no. Yes. Sorry, I couldn't hear you.
It's also called the null set or do I know?
Yes. So the empty set, the null set, all of these things, right? Importantly, right, the null set we can write a couple different ways. You can put it with the squiggly brackets right next to each other, right? You can put it, again, sorry to any of our Scandinavian people out there, right? You can write it with this sort of zero with a line through it. I'll often do it this way just because it's a little bit easier to read. Right? Yes?
Do we use empty sets or go like nuclear? Or like, what do we use it for?
Good question. So empty sets are kind of weird. They're kind of a theoretical posit that honestly we've added to the set theory because it makes the machinery work. Without it, a lot of the rules have to be completely revised. By having this sort of null collection, everything works a lot better. Strictly speaking, you can have set theories that don't have it. Just shit gets real ugly real fast. So it's a useful posit in many ways. Yeah.
Could you have a singleton set of an empty set?
Absolutely, right? So the singleton set of the empty set, we could write so again, this actually highlights again the difference between membership and being a subset, right? So how many members does this set have? It's got one. Almost. This set has one, and it's the collection, the one member of this set is the collection with nothing in it, right? If you want to think about this kind of metaphorically, this is basically a box, and inside the box is an empty box. But again, this is actually a useful point, right? Of driving home the difference between a set being a member and its members being members. Right? The null set is a member of singleton null set. Right? But of course, its members aren't, because it doesn't have any. Okay, so we'll talk more about this again as we kind of keep going. Yes?
I'm sorry.
No.
Is it possible if you put the two squiggly brackets?
Yeah, if you just-
I don't look inside of them. It's just you saw that there was.
If there's nothing in the middle, then you know that it's just another way to write the empty set. Right? So yeah, these are different. You can also do this several different ways. This is the kind of terminology I'm most familiar with. So I'll write them this way. I have a preference to do the zero with a line through it because it's very easy to start to blur the squiggly brackets together. So the empty set is weird, no lie. But one cool thing about the empty set is it is a subset of every set. The empty set is a subset of every set, which makes sense. It's less than or equal to every set. It has fewer or equal to members compared to everybody. You've got one? Cool, I've got less. You've got none? Cool, we have the same. We are the same. Yeah. It's okay.
Oh, is the empty set the subset of the empty set?
Yes.
Then how can the empty set be empty?
Good. So remember, less than, right? So first thing, subsethood isn't the same as membership. Remember, right? Subsethood is just, do I have fewer or equal to number of members? Right? So in that case, it's the same number. None. Right? So here's the argument. Here's the argument for why the empty set's a subset of everyone. Right? Basically, just kind of go through the reasoning. For any x, it's not the case that x is a member of the empty set. So for all x, the antecedent of the subset condition is going to be false. That is, right, for all x, x is a member of the empty set, then it's a member of T. Well, it's not a member of the empty set, so cool. The empty set must be less than. It turns out to be a subset, even of itself. But that's, again, okay. Remember, to be a subset is to be less than or equal to. But to stress, this does not mean that the empty set is a member. It's not in these collections, or at least not all the collections. It can be in some. Yes?
And an empty set is also a superset of itself.
Yeah. Because it's greater than or equal to, but it's the only one that it's a superset of. So again, to kind of drive home the difference between this membership and subset relationship, right? If we look at this set, one right here, the empty set is a member. It is in this collection. This collection which has two members, the empty set and Socrates. The top one, right? It's a member and it is a subset because it is in this box. There it is, right there. Yeah.
But a set, and if its member being an empty set, does it still have one member then?
It still does. It has that collection. So this is, again, the first move. This is why we started by talking about the idea of collections as something over and above their members. Right? The empty set has no members, and yet it is. It is, again, if you want to take the really bad joke, right? It's the number of people who love me, right? Like, it's nobody, right? It's empty, but it's still a collection. It's just a collection in want of a member, right? So again, this is a deep, deep point, but if we get the difference between membership and subsethood, we're off and running. Okay, cool. So again, this is kind of the background for basic set theory, right? I'm not teaching you a lot about the actual machinery in a way, but I want to talk about, if you like, the philosophy of maths that's lurking behind it. So once we have a bunch of sets, we can do some operations on them. And this will be familiar, I suspect. So one operation we can do for any two sets is to find their union. And we can write the union operation as this sort of big U, right? And the union of two sets is basically just anything that's a member of either of them. Right? So the union of the sets containing George and Ringo and the set containing John and Paul is John, Paul, George, and Ringo. Right? Anything that's a member of either of the two. So if you want to think about it in terms of Venn diagrams, it's basically, hey, are you in either circle? So union is or, which is handy. Right? Union's or. Are you in the club at all? We don't care which one. Right? Yeah. We use, well, so for union, we use this kind of U. It's written in a slightly different font. It'll always be clear. It's a union function. Right? So again, union is member of one or the other. On the flip, we can also look for the intersection. The intersection is where you're in the overlap, where you're in both. Yeah.
Can you use the logical or symbol?
Yeah, so it was just, it's when we're doing the set theory, we always want to use the operator, right? The kind of the U here. But it's broadly the same as the or. Oh, yeah. You can write the disjunction here. That's fine. Yeah. And the same thing here for this. You can write the conjunction for and. Right. So again, intersections, finding the overlap. Right. Who's in both sets? Right. So the intersection of the set with George and John and Paul is just John. Now let me stress, when I'm saying it's just John, what I really mean is it's the set with just these members. The same thing too, to go back a slide, with the union. The union of these two sets is the set containing these objects. It isn't these objects alone. It is the collection with these as members. So again, whenever we're doing these operations, we should always get a set, not individuals. So the union is just, hey, are you in either? The intersection is, hey, are you in both? And a last operation we can also define, that we'll concern ourselves with, is difference. And the difference is basically, are you in the remainder? I take out the overlap and I look at who's left. So the difference, right, is all the set of things that are in our first one and not in our second one. So we have this set with George and John, and we have John and Paul. Right? And what we do is we take out anything that's in this one, that's also in this one, and look at the set of what's left. And that gives us the difference. So difference is effectively something like subtraction, right, or remainder. In 3 operations: union, are you in either? Intersection, are you in the overlap? Right? And difference, are you in what's left over after I take out the overlap? These operations are wonderful because basically with these 3, we can pretty much define up almost all of mathematics, which is really cool. So again, we have the basic idea of what membership is as a relation. We have being a subset / being a superset. Different relations, both important, but different relations, work in different ways. And we have these operations that we can do: the union, the intersection, the difference. The last thing I really want to talk about here is a notion of power sets. This is also an extremely useful function or operation we can perform. And we'll write it with this fancy little p, right? The power set operation gives us a new set. We feed in a set, and the power set operation gives us the set of all of our initial set's subsets. So I feed in the set containing A, B, and I get out a set whose members are all of the original set's subsets. So in this case, we get the null set, because remember, it's a subset of every set. We get singleton A, singleton B, and the original set we started with, because everything is less than or equal to itself. Similarly, if we take the set ABC as members, we get out this thing. And again, what is this thing over here? It is the collection of all the subcollections. How many different ways could we break this party up? Right? Well, you could leave it the way it is. You could get rid of everybody. There's our 2 extremes: the empty set, the original set you started with. And then you think about all of the different ways you could cut it up. More generally, any set with n members has 2 to the n subsets. So maybe an interesting place to start, right? And a fun little question. If every set is 2 to the n, right, what's the power set of the empty set? It only has the empty set as a member. The power set of the empty set is singleton empty set. Because what's the only subset in the empty set? The empty set itself. Again, so power set operations gives us, what are all the subcollections? Give me all the different subcollections. How could we box up all the things that are in there in different ways? Yes?
So like with the box thingy, we have an empty box, and so it's 2 to the power of the box.
In some sense, right? So basically we're asking, hey, how many different ways could we box this box up? Just the one. We just take the box that's empty,
Yeah.
and we drop it in a box.
Another box. Okay.
And that gives us this. Okay. So how we doing so far? We feeling okay? Fair. Again, this is fun stuff. This is the kind of thing that, yeah, this is the beginning of the fun stuff. So last thing before we'll get to our break just after this. I want to quickly talk about cardinality. So this is something we'll use in a few minutes, but I just want to introduce this notion. So this is just the idea: the cardinality of a set is the number of members the set has. Right? The cardinality of the set is the number of members it has. Right? So what's the cardinality of the empty set? 0, right? And what's the cardinality of singleton Socrates? Nice. Interesting question. What's the cardinality of power set of singleton Socrates? Yeah, it's got the empty set and it's got singleton Socrates, right? These are the ways you could sub-collect up singleton Socrates. Nice. Okay. Again, cardinality is basically how many members do you have? So this is really the kind of core of what I want to get to you, right? You will see these notions come up again, and I hope that this is at least giving you some kind of feel for some of the things that you can do with set theory, right? We haven't done much machinery-wise, but I want to introduce you to the notions. Yes?
Can we just say again what's the cardinality of the first one?
Cool.
Sorry, makes sense.
Because it got no members. Right? So it is 0. Now I'm going to skip this. So there's some other kind of notions you can have. We can talk about the idea of pure sets, that is, sets that have no individuals as members. We're not going to talk about this. I just want to kind of put it up there. We can use pure sets in various philosophy of maths ways. Anyone who's interested can come and talk to me about this, but don't stress. I'm just going to go over it. Right, we're not going to talk about it. Right. We can also use sets to express ordered pairs. Right. Again, don't stress. I'm not going to talk about this. This is just to kind of flash it up. If you're interested, we can talk about it later. Right? We can also, and this is the last thing I want to do, talk about functions. Now, I imagine that you guys are very, very, very familiar with functions. Right. From a philosophical perspective, functions are very interesting. So as we understand them, a function is a relation that unambiguously maps one collection to another. You will note, implicit in this is we understand functions in terms of sets. Functions are mappings between sets. Right? So the easiest kind of function to get your head around is a seating assignment, right? It's a function for members of one collection, students, to another collection, desks or seats. Right? And a good function should give 1 to 1 there. But of course, people screw up. If you want some terminology, and I expect people are familiar with this, we can talk about the first collection being the domain and the second collection being the codomain. Is that familiar terminology? Have you guys heard that in other courses and things? Okay. Okay. It's just the things you are mapping to, right? That's all that matters, right? So when it comes to types of functions, you can have a bunch. But the two that are probably the most interesting are many-one or isometric. right? Many one is a relation that unambiguously maps one collection to another such that several members of the first are mapped to one member of the second. Right? So, apropos of what we were talking about earlier, grading is often one. Multiple people, multiple students, can be mapped to the same score. So it's a many to one function. Another one is tutorial assignments, right? There's a bunch of people who are assigned to a single tutorial together, right? Because otherwise we would have a hell of a lot of tutorials. So many one, cool, many to one. You can also have one many, where you have one individual from our first one mapped to a bunch of different in the codomain. Contrast to the many one is an isomorphic one. This is a one-to-one correspondence, a function that gives us a one-to-one mapping. And importantly, it's not just a mapping, but it also aims to preserve the structure in some way of the former. So we don't want to just go one-to-one mapping willy-nilly, right? But instead we map them one-to-one in a way that somehow kind of preserves some structure. So a great example here is an ordnance survey map. Right? The distance between map points is proportionally the same as the distance between physical points. So we have a one-to-one mapping, an isomorphic mapping of points on the map to real-world places. But we also do the one-to-one mapping in such a way as to preserve distance. Because otherwise it's a fucking useless map, right? We want it to be able to at least preserve the structure. Isomorphic functions are super useful, super philosophically interesting, super mathematically interesting. Right? But again, what's important for our purposes is to know the difference between these. Right? So again, we've introduced the basic conceptions of some set theory. We've talked about the idea of using set theory to understand functions. And we talked about these two functions. So let's take a break. We're at 40. So why don't we take a break till 50, right? So 10 minutes. We'll come back at 1:50, and then we'll go from here. Okay?